Welcome back to the deep dive. We are doing something a little different today because we are tackling a problem that I think every single person listening has smashed their head against probably in the last week.
Oh, absolutely.
It's the needle versus the haystack problem, but specifically how we interact with artificial intelligence.
It is, I think, the defining problem of the current generation of large language models.
Hmm.
And it's deceptively simple, which is what makes it so frustrating.
Right, because on the surface, AI feels like magic.
Right.
If I have a 10,000-page PDF of, I don't know, legal contracts, and I upload it to a chatbot and ask, what is the termination date in clause 4.2?
It nails it.
Instantly.
Instantly. It finds that needle.
That's precision retrieval. And honestly, we've pretty much solved that. If you need a specific fact, a date, a name, a quote, something located in a specific place, modern AI is actually better than a human at that. It's faster, it doesn't get tired. But, and this is the massive but that we are unpacking today, if I hand that same AI a library of books or a massive dump of corporate Slack messages, and I ask a question like, how has the culture of this company shifted regarding remote work over the last 3 years?
It completely falls apart.
It just chokes.
It fails. It either hallucinates or it gives you a generic, wishy-washy answer that's useless, or it just says, I can't look at all of that at once.
Exactly. It's great at finding the needle, but it has no idea what the haystack is actually made of. It can't describe the hay.
It can't do what we're calling global sense-making.
And that brings us to the paper we are breaking down today. It is from Microsoft Research, titled From Local to Global, a GraphRAG approach to query-focused summarization.
GraphRAG. It's a term you're going to be hearing a lot more of, I promise you.
And the mission for this deep dive is really to unpack the methodology of this paper. We aren't just going to look at the shiny results at the end. We are going to tear apart the engine. We need to understand how they built this system step by step, because they essentially had to rewire how an AI processes these massive data sets to solve this very sense-making problem.
I think that's the perfect way to put it. They moved from what is essentially a search engine model to a research analyst model. And the engineering behind that shift is, well, it's fascinating because it combines old school network science with the most cutting edge LLMs.
So let's set the stage. To understand why GraphRAG is a breakthrough, we have to first understand why the current standard, what we call standard RAG or vector RAG, fails so badly at this.
Right. You need the baseline.
So I use RAG tools all the time. For listeners who might not be building these apps day to day, RAG stands for Retrieval Augmented Generation. Basically, I ask a question, the system searches my documents, it finds the relevant bits, and then it feeds those bits to the AI to write an answer.
That's the basic workflow, yeah.
So why does that break? Why does that simple logical process break when I ask a big open-ended question like, what are the main themes in this data set?
It breaks because of how vector RAG finds information. It's all in the retrieval part. When you ingest documents into a standard RAG system, you're turning the text into vectors.
Into numbers.
Right. Long lists of numbers that represent meaning in sort of multi-dimensional space. We call these embeddings. The idea is that concepts that are similar will be mathematically close to each other in that space.
So dog is close to puppy, cat is close to kitten.
Exactly. Quarterly revenue is close to financial performance. So if you search for quarterly revenue, the system looks for text chunks whose number lists, their vectors, are mathematically close to the vector for quarterly revenue.
Okay, that makes perfect sense. It performs what's called a nearest neighbor search.
Precisely. It grabs the top 5 or 10 chunks of text that match your query, we call this top K retrieval, and sends only those to the LLM.
I see where this is going. If I ask, what is the termination date? The answer is probably in one specific paragraph. So retrieving the top 5 chunks that talk about termination works perfectly.
Correct. It's a local question. It has a local answer.
But now, ask your question again. What are the main themes?
What are the main themes?
Where is the answer to that question located in the document?
It's nowhere, and it's everywhere.
Exactly.
There is no single paragraph in a million-word data set that conveniently says the main themes are X, Y, and Z. The themes are an emergent property of the entire data set. They're scattered across thousands of conversations, documents, reports.
So if the system tries to do a top K search for the phrase main themes, what does it actually find?
It finds nothing useful. I mean, if you're lucky, it might find a table of contents, or it might find a random sentence where someone happened to use the word theme, but it fails completely to capture the aggregate picture.
It's like asking, what is the mood of this party? And the AI walks over to 2 people standing by the cheese dip, listens to them for 10 seconds, and reports back. The mood is specifically concerned with whether the brie is room temperature.
That's a perfect analogy. You get a tiny, unrepresentative snippet. You miss the vibe of the whole room.
It is a failure of scope.
It's a failure of distribution. Standard RAG assumes the answer is local, that it's contained in a small chunk of text. But these sense-making questions require a global view. You have to read the whole library, not just 5 random pages.
Okay, but we can't just feed the whole library into the AI. I mean, we keep hearing about these new million token context windows, but even with those, it's incredibly expensive, it's slow, and the models still get confused.
They absolutely do. The lost in the middle phenomenon is real. Research has shown that if you feed an LLM a novel and ask a question about a detail in chapter 12, it often forgets it because it was buried in the middle of the context. So just making the window bigger isn't the answer.
We need a smarter way. We need a way to compress the meaning of the library without losing all the critical connections between the ideas.
And that is exactly where GraphRAG comes in. The paper's technical goal is something they call query-focused summarization, or QFS.
QFS. So that just means generating a summary that answers a specific user's intent, but over a massive corpus of text.
Correct.
Yeah.
And the mechanism they use to achieve this is a knowledge graph.
Now, I want to be careful here because knowledge graph is a buzzword that gets thrown around a lot in tech. We have a graph. Usually just means we have a messy database.
That is often true, unfortunately.
So what is distinct about the methodology here? How are they actually building this thing? Because the paper breaks it down into a very specific, very deliberate pipeline.
The methodology is distinct because it's a two-stage process. Stage 1 is indexing. This happens completely offline. It's the prep work. This is our research analyst reading all the books and taking meticulous notes before you even walk into the room.
And stage 2?
Stage 2 is querying. That's when you actually walk in and ask the question.
And that's the big difference. Most RD systems do all the heavy lifting at query time.
Exactly. Standard RD is lazy. It waits for you to ask, then it panics and runs to the shelf.
Hmm.
GraphRAG is proactive. It organizes the entire library first. And the intuition behind that organization relies on a concept from network science called modularity.
Modularity. Okay, break that down for us.
It's a really simple idea at its core. If you map out any complex system, be it a social network, biological proteins, or in this case, a corpus of documents, you find that the nodes, the things in the network, they don't connect randomly.
Okay.
They form clusters. They form communities.
Like cliques in a high school.
Or departments in a company. Or different topics in a research field. Information is clumpy. You'll have a dense cluster of information all about Project Alpha, and it's only loosely connected to another dense cluster about HR policy, which is in turn loosely connected to budget planning.
So the intuition is, if we can identify these clusters first, and then maybe summarize each cluster individually, we can build a map of the data that actually makes sense to a human.
Precisely. Instead of trying to read and summarize the whole world at once, which is impossible, we first summarize the continents. Then we go inside those continents and summarize the countries, then the cities. It creates a hierarchy of understanding from the global all the way down to the local.
Okay, I buy the theory. It sounds great on a whiteboard, but I really want to get into the gears now. Section 3 of our outline is the methodology. The paper lists this out step by step, and I want to walk through it.
Let's do it.
Step 1, source documents to text chunks.
This is the foundation. You can't do anything until you take your massive documents and break them into manageable pieces.
Now, in standard RAG, people fight about chunk size constantly. Is it 200 tokens? 500? 2,000? There are whole blog posts about this. What did the authors choose here and why?
They settled on chunks of about 600 tokens. That's roughly, say, 400 to 500 words.
Okay, why that specific size?
It's a really important trade-off. You need the chunk to be long enough to contain complete thoughts and relationships. If you chop it up into single sentences, you lose all the context.
Right. You might have one sentence that says he signed the deal, but the previous sentence that identifies he as Elon Musk is now in a completely different chunk.
You've lost the connection. So you need enough length to capture the who, what, where, when, why of a particular event or idea.
But not so long that the LLM gets lazy.
Exactly, that lost in the middle problem again.
Yeah.
If you give the model a 10,000-word chunk, it's going to forget what was at the beginning by the time it gets to the end.
Yeah.
So 600 tokens was their sweet spot, where the extraction is high fidelity, but the context is still preserved.
Okay, so we've got our neat piles of 600 token chunks. Now we move to step 2, element extraction. This is where the LLM actually starts reading the text.
This is where we stop treating text as just strings of characters and start converting it into structured data. The system feeds a chunk to the LLM and gives it a very specific prompt. And that prompt basically says, read this text. Identify all the entities and all the relationships you can find.
And entities are things like people, organizations,
Yeah.
places, right? The nouns.
Yes, but also more abstract things like logical concepts, events, biological targets, whatever fits the domain of your data. And the relationships are the connections. They are the verbs. John Smith, entity, is the CEO of relationship, Acme Corp entity.
Okay, now I want to drill down here because the paper mentions a specific and really clever technique they used called self-reflection. They didn't just ask the LLM once and trust it.
No. And this is absolutely critical to the quality of the final graph. We all know LLMs can be flaky. Sometimes they get bored. Sometimes they miss the third person mentioned in a paragraph for no good reason. So the authors implemented a loop, a quality control loop.
Walk me through that loop. How does it work?
So in the first pass, the LLM reads the text and outputs a list of entities and relationships. It says, okay, here's what I found.
Simple enough.
Then the system takes that list that the LLM just generated, and it takes the original text, and it feeds them both back into the LLM with a new prompt. And that second prompt effectively asks, okay, look again, here is the original text, and here is what you found the first time. Did you miss anything? Is there anything in this text that should be extracted but wasn't on your first list?
It's like a teacher standing over your shoulder saying, are you sure? Check your work.
It is exactly that. And the paper found that this grounding pass, this self-reflection step, significantly increased the recall, which is the technical term for the number of valid entities found. Without it, the graph was too sparse. It was full of holes. It missed crucial connections. With the self-reflection, the graph became dense and rich and much more accurate.
That seems like it would double the cost, though. You're calling the LLM twice for every single 600 token chunk in your data set.
It does. It absolutely increases the cost during the indexing phase. That is the trade-off. You are choosing to pay more upfront to build a much better, much more reliable map so that your answers later on are actually accurate and not based on incomplete data.
Quality costs money.
Always.
The paper also mentions extracting claims. How is a claim different from a simple relationship?
It's a great question. A relationship is usually structural. It's a simple connection. A is connected to B. A claim is a more complex statement of fact that often involves those entities, but it has a time component or a status component. It adds narrative.
Can you give me an example?
Sure. A relationship is Acme Corp acquired Beta Inc. A claim might be something like, Acme Corp has been facing antitrust scrutiny since Q3 2023 as a direct result of the Beta Inc. acquisition.
Ah, I see. So it captures the narrative and the status, not just the static connection. It tells you what's happening with that connection.
Correct. And this is vital for sense-making. If your question is, what is the status of Project X? You don't just need to know who is working on it, which are the relationships. You need to know that it is currently behind schedule and over budget. Those are the claims.
Got it. Okay, so to recap this stage, we've chunked the text, we've used an LLM to extract thousands of entities and relationships, and we've verified them with a self-reflection loop to make sure we didn't miss anything. Now we get to step 3, graph construction and community detection. Now we get to step 3, we have a giant bucket of Lego bricks. Now we have to actually build the castle.
Right. And this is where the graph in GraphRAG comes to life. We take all those entities we extracted, let's say we have 10,000 of them, and they become the nodes in our graph, the little dots. The relationships become the edges, the lines connecting the dots.
And the paper talks about these being weighted edges. What does that mean?
It means that not all connections are created equal. If host speaker and expert speaker are mentioned together in one document, we draw a line between us. We have a connection. But if we are mentioned together in 500 different documents...
That's a much stronger connection.
An incredibly strong connection. So the system counts the frequency of these co-occurrences and assigns a weight to the edge. You can think of it like drawing thicker lines for stronger, more important relationships.
Okay, so we've built this massive, hairy spider web of data. If you tried to visualize it, it would probably just look like a giant hairball. How do we make any sense of it? This is where the Leiden algorithm comes in.
The Leiden algorithm. This is the heart of the modularity approach we talked about earlier. If you look at that giant hairball of a graph, it's not uniform. There are clumps. There are dense patches. The Leiden algorithm is a very clever mathematical process designed to automatically identify those clumps.
How does it know what a clump is? What's the logic?
It tries to achieve something called modularity maximization. Put simply, it tries to draw circles around groups of nodes in a way that the nodes inside the circle are very, very densely connected to each other, but have very few connections pointing outside the circle.
So going back to the company analogy, the engineering team all emails each other constantly. That's a ton of dense internal connections, but they only occasionally email the legal team. Those are sparse external connections.
Exactly. The Leiden algorithm finds the engineering team cluster automatically, purely based on the structure of those connections. It has no idea that they're engineers. It just knows they all hang out together in the graph.
But the really crucial part that the paper emphasizes is that this is hierarchical. It's not just one flat layer of groups. It doesn't just find engineering and sales and stop.
This is the local to global part of the title in action. The algorithm runs recursively. At level 0, you have the entire dataset, the whole hairball. At level 1, Leiden runs and might break the graph into 5 huge communities. Let's say engineering, sales, marketing, legal, and HR. Then it goes inside the engineering community and runs the algorithm again on just those nodes. That's level 2. And it finds smaller, more specific clusters. Back-end team, front-end team, DevOps team. Who see? Then it goes inside the engineering community and runs the algorithm again on just those nodes. That's level 2. And it finds smaller, more specific clusters. Then it could go inside backend to level 3 and find clusters related to specific microservices.
Wow. So it builds a ladder of abstraction from the most specific details all the way up to the highest level themes.
Precisely. And this hierarchical structure is what allows the system to answer questions at different levels of granularity. You can ask about a specific microservice, or you can ask about the entire engineering department. The structure is there.
Which leads us to step 4, which I honestly think is the most clever part of this whole paper. Community summarization. This is where the real magic happens.
I agree. This is the index innovation that sets it apart. In a normal graph database, you would just leave the nodes and edges there and then try to query them later. GraphRAG says, no, that's inefficient. We are going to pre-process. Once the Leiden algorithm identifies a community, let's stick with our example, level 2 community, the back-end engineering team. The system gathers up all the data associated with the nodes in that community.
So all the entities, all the claims, all the relationships.
All of it. And it sends that entire package of information to the LLM.
And it asks it to write a report.
Yes. The prompt is effectively, review all this structured data for this specific community and write a summary. What is this group about? What are the key themes? What are the major claims and events associated with these entities?
So it generates a human-readable summary for the back-end team. And it does this for every single community it found, at every single level of the hierarchy.
Every single one. It generates potentially thousands of summaries. It writes a summary for the offensive line. Then it might use that summary as context to help it write the summary for the football team.
Mm-hmm.
And then it uses the football team summary to help write the one for the entire athletic department.
It's rolling up the insights from the bottom to the top.
It's pre-computing the understanding. So now your haystack isn't a million disconnected facts anymore. It's been organized into neat, labeled bales, and every single bale have a cover sheet, a summary, explaining exactly what is inside it.
This sounds incredibly expensive from a computational standpoint. You're generating thousands of summaries before a user even asks a single question.
It is a front-loaded cost. It's a significant investment during the indexing phase. You are making a bet that the cost of building this incredible index will pay off down the line because the querying will be faster, smarter, and profoundly more accurate.
It's a big bet.
It's a big bet, but yes, compared to just dumping text into a vector database, this is a much heavier computational lift during the setup.
But the payoff is what we see in section 4, answering the question. So the index is built. The research analyst has read the entire library and written all the Cliff's notes. Now I, the user, walk in. I ask a big, hairy, global question. How have interpersonal conflicts affected the project timeline? Now I, the user, walk in. I ask a big, hairy, global question. How does the system use this beautiful library of summaries to answer that?
It uses a classic and very powerful computer science process called MapReduce.
Okay, let's break that down. First, the map phase. What happens?
In the map phase, the system looks at your question. Then it looks at its library of community summaries, and this is key. It doesn't look at the raw 600 token text chunks anymore. That would be way too slow and expensive. It only looks at the summaries it created.
Does it look at all of them? Or does it filter them first?
It does an initial filtering, maybe using a lightweight vector search on the summaries themselves to find the ones that seem most relevant. Let's say it grabs 20 different community summaries from various levels of the hierarchy that mention things like conflict, timelines, delays, projects.
Okay, so it has 20 candidate summaries.
Right. Now it processes them all in parallel. That's the map part. For each of the 20 summaries, it makes a separate call to the LLM. He says, here is the summary for community A. Read it. Does this summary contain information that helps answer the user's question about conflict and timelines? If yes, write a partial answer based only on this summary. And this is the secret sauce. Give yourself a helpfulness score.
A score? The LLM grades its own work.
Yes, from 0 to 100. It's a self-evaluation. It might say, I found nothing relevant about conflicts here, so my helpfulness score is 0. Or it might say, wow, this summary details a massive conflict in this department that delayed a project by 6 months. My helpfulness score is 100.
That is brilliant. It's an automated noise filter.
It's a fantastic noise filter.
Yeah.
Because a lot of communities simply won't be relevant. The summary for the company cafeteria menu community has nothing to do with project timelines. So that gets a 0 score and is immediately discarded.
So after the map phase, we're left with a handful of high-scoring partial answers from different parts of the organization's data. One from marketing that says there was a conflict over the ad campaign. One from engineering that says we're delayed because of a dependency. One from legal saying we're fighting a patent troll. Then comes the reduce phase.
The reduce phase is the final synthesis. The system takes those top-scoring partial answers, say the top 5, and combines them into a single context window. Then it makes one final call to the LLM and says, here are 5 different verified insights from various parts of the dataset. Your job is to combine these into a single, coherent, well-written global answer.
And because it's drawing from these different diverse communities, you get that true global view. You don't just get the first thing that matched a keyword, you get a mosaic of perspectives.
You get the forest, not just a single tree. You get a synthesized narrative that draws from the entire dataset, but it's grounded in the structure of the graph and the facts from the summaries.
Let's pause here on the cost again. We established that indexing is expensive, but what about this querying phase? Is MapReduce expensive?
It's not cheap, let's be clear. You are making multiple LLM calls in parallel for the map phase, maybe 5, 10, 20 calls, and then another powerful call to synthesize it all in the reduce phase. It is certainly more expensive per query than a simple vector search, which is basically just math plus one LLM call.
So why do it? If it costs more per question, what's the justification?
Because vector search gives you the wrong answer, or at least an incomplete and misleading one. If you ask a complex sense-making question to a standard vector ARG system, it might cost you pennies, but the answer is garbage. It's useless for any real decision-making. GraphRAG costs, let's say, a few dollars per query, but the answer is comprehensive, nuanced, and actionable.
It's a value proposition, not a cost one.
Exactly. For enterprise applications, if you're a financial analyst, an intelligence agent, or a lawyer doing discovery, paying a few dollars for a report that would take a human analyst 2 weeks to write is an absolute unbelievable bargain.
That puts it in perspective. The competition isn't Google search. The competition is a human analyst earning $100 an hour.
That's the correct frame.
Okay, let's move to section 5. Evaluation and assumptions. We've established that it sounds very cool. It sounds powerful. But does it actually work? And, maybe more importantly, how do we know it works? Evaluating summarization is notoriously difficult. If I ask, what is the capital of France? There is a single right answer. If I ask, what are the themes in this novel? It's subjective.
It is deeply subjective. So the authors had to get creative. They used what is quickly becoming the gold standard for this kind of subjective evaluation. LLM as a judge.
Using AI to grade AI, it sounds a bit circular.
It sounds circular, but it's actually becoming standard practice in research because it's more consistent than human raters.
Okay.
They took a data set, I believe they used podcast transcripts and news articles, and they used an LLM to generate a set of broad, sense-making questions a user might ask.
Okay.
Then they had GraphRAG generate answers to those questions.
Yeah.
And they had a standard vector RAG system generate answers to the same questions. Then they took both answers, anonymized them so the judge wouldn't know which was which, and fed them to a powerful third-party model like GPT-4.
A blind taste test.
A blind taste test, exactly. And they asked the judge LLM to score the two answers head-to-head on 4 specific metrics.
What were the metrics?
The first was comprehensiveness. Did the answer cover all the relevant aspects and details from the source? The second was diversity. Did it provide different perspectives and a richness of information? Third was empowerment. Did the answer actually help the user understand the topic better and make an informed judgment? And the last one was directness. Was it concise and to the point?
Okay, let me guess. GraphRAG won, hands down, on comprehensiveness.
It crushed it. It wasn't even close.
Yeah.
Because it scans the whole graph structure, it finds details and connections that VectorAg completely misses. It also won decisively on diversity and empowerment for the same reason. It just gives you a much richer picture.
What about directness?
That's the interesting one. Standard VectorAg actually won on directness.
Really? Why?
Because VectorAg is blunt and simple. It finds 3 sentences in a document that match your keywords, and it regurgitates them. The answer is very short. GraphRAG, by contrast, tends to write longer, more nuanced, more detailed answers because it's synthesizing from multiple sources. So if your only definition of directness is short as character count, then yeah, VectorRAG wins.
But in a sense-making context, short is usually bad. You want the nuance, you want the detail.
Precisely. It's a bit of a misleading metric in this context. If I just want a quick fact, I should keep using VectorRAG.
Absolutely. If your question is, what is the date of the merger? Do not use GraphRAG. It is complete overkill. Use a search engine. But if you want to understand why the merger happened, how the employees felt about it, and what the long-term implications are, GraphRAG is profoundly superior. Okay, let's talk about the assumptions. Every model has an Achilles heel. What are we assuming has to be true for this whole beautiful system to work?
We are making one massive critical assumption about the quality of the summaries. Remember, the final answer the user gets is generated from the community summaries, not from the raw text. We are playing a game of telephone. The LLM reads the text, extracts entities. Another LLM summarizes those entities. A third LLM reads those summaries to answer your question.
So if the LLM hallucinates while writing the summary for the marketing community way back in the indexing phase,
that hallucination is now baked into the index. It becomes a permanent, trusted fact in your knowledge graph. And when the query phase happens months later, the system will read that flawed summary and treat it as absolute truth, incorporating the hallucination into your final answer.
Garbage in, garbage out. If the foundation is poisoned, the whole house collapses.
Exactly. That is why the authors emphasize that self-reflection step during the initial extraction so much. You have to be maniacal about data quality at the start. If your graph is built on a foundation of hallucinations, your answers will just be very confident nonsense.
Another assumption, it seems to me, is that communities map to themes.
Yes, that's a good one. We are assuming that because the Leiden algorithm grouped these nodes together based on mathematical connectivity, they therefore represent a coherent semantic topic. And, 99% of the time that's true. It works remarkably well. But sometimes graph algorithms can find weird, spurious clusters that make sense mathematically but look like complete gibberish to a human.
So you might get a community that's just a random grab bag of people who happen to share a common generic name like Smith, and it has no real thematic coherence.
It's possible.
Yeah.
And if that happens, the MapReduce step should theoretically filter it out with a low helpfulness score because the summary of that community would be nonsense. But it's an inefficiency in the system you have to be aware of.
Let's move to our last big section here, comparisons. We've compared it to VectorAG, but there is another baseline we need to consider. Why go through all the trouble of building a graph at all? Why not just take all the text chunks, all 10,000 of them, and brute force it? Just feed them to the LLM in batches and say, summarize this whole thing.
The paper calls this source text summarization, or a global summarization baseline. It's basically skipping the graph and just using the MapReduce technique on the raw text itself.
Does it work?
It actually works quite well in terms of pure quality. If you are willing to have the LLM read every single document every time you ask a question, you get a very good comprehensive answer. The quality is comparable to GraphRAG's output.
So why build the graph? If the quality is the same, what's the point?
Cost and scalability.
Okay.
In 2 words, if you do source text summarization, you are processing the entire data set, every token, every single time you ask a question. If your data set is 1 million tokens and you pay your LLM provider per token, asking 10 questions will bankrupt you. It's not a viable strategy.
Right, whereas GraphRAG processes the entire data set exactly once when it builds the index.
And then querying is vastly cheaper. You only have to read the summaries, which are a tiny fraction of the original text volume.
Yeah.
The paper found that for high-level, root-level questions, GraphRAG used something like 97% fewer tokens at query time than the brute force method.
97% fewer. That's not a small optimization. That is the difference between a viable product and a research prototype.
It's everything. It makes global sense-making economically feasible at scale.
And there's a scalability factor too, isn't there? As the data grows.
This is the really cool part, I think. If your dataset doubles in size, a standard vector array system actually gets worse because your top 5 retrieval now covers an even smaller percentage of the total pie. But with GraphRAG, even if the data doubles, the number of high-level themes might remain stable.
What do you mean?
Well, think about it. If you add another year of company emails, you'll have more details at the bottom of the graph, more level 3 or 4 communities about specific projects. Yep. But the number of level 1 communities, the big departments like engineering, sales, HR, that number doesn't necessarily double. It stays roughly the same.
So the complexity of the summary index doesn't explode just because the volume of the raw data exploded.
Exactly. The system's complexity scales with the complexity of the ideas in the data, not just the raw volume of words. And that is a much more graceful way to scale.
Okay, we are coming to the end of our deep dive. I want to try to summarize this entire complex methodology in one coherent thought. You can grade me.
Go for it. Let's see it.
Okay. We start with a messy pile of documents. 1, we smash them into consistent 600 token chunks. 2, an LLM reads each chunk and pulls out entities and relationships using a self-reflection loop to double-check its work and catch what it missed. 3, we use all those extracted elements to build a massive web-awaited graph where stronger connections have thicker lines. 4, we then use the Leiden algorithm to find the natural cliques or communities in that graph, and we do it hierarchically at multiple levels of abstraction. 5, an LLM then writes a CliffsNotes summary for every single one of those communities, creating a pre-computed library of insights, that's the index. Then when I come along and ask a big sense-making question, that's the index. Then when I come along and ask a big sense-making question, 6, we use a MapReduce process to scan the relevant summaries, have the LLM score them for helpfulness to filter out the noise, and then synthesize the best parts into a single, cohesive, global answer.
A+. You nailed it. That is the pipeline from start to finish.
It really feels like a fundamental shift in thinking. We've spent the last 2 years treating AI as a search engine on steroids. This methodology treats AI as a cognitive architecture. It's about structuring knowledge, not just indexing words.
It moves AI from mere fact retrieval to holistic understanding. And that matters because the hardest problems we face in medicine, in policy, in law are rarely about finding a single date in a document. They're about understanding trends, contradictions, and complex interwoven narratives.
Sensemaking.
Sensemaking. We are finally teaching machines how to make sense of our world, not just how to read it.
I want to leave our listeners with a final thought, a bit of a provocation to chew on. We've talked about applying this to corporate data or libraries of scientific papers, but we know GraphRAG works by detecting communities using the Leiden algorithm. And what that algorithm does is find clusters of nodes that talk to each other a lot and mostly ignore the ones that don't. So, what happens if we feed this system the entire internet's discourse on a deeply polarizing political topic?
Oh, that is a fascinating and slightly terrifying thought.
Would the Leiden algorithm naturally map the echo chambers? Would we see the graph automatically partition itself into a community red and a community blue that are incredibly dense internally, everyone retweeting and linking to each other, but have almost no edges, no connections, crossing the divide to the other side?
You would essentially generate a topological map of polarization. You wouldn't just know that polarization exists. You could measure it. You could see the structural gap. You could identify the few critical bridge nodes that do try to connect the two sides.
And then, using the summarization step, you could ask the AI, generate a summary of the core axioms and beliefs of community red based on their own words, and then do the same for community blue. Could you use GraphRAG not just to summarize a single body of text, but to empathize, to understand the structure of the other side's reality as derived from their own data?
You're turning vibe into data. You're turning that abstract emotional feeling of us versus them into a navigable, quantifiable map. That is an incredibly powerful tool, for good or for ill.
Turning vibe into data. I think that is the perfect place to stop. This has been a dense one, but I think it's a crucial one. This graph approach might just be the missing link that takes AI from a cool toy to a genuine intelligence partner. Expert, thanks for unpacking the graph with me.
Always a pleasure. This was fun.
And to you, the listener, thanks for taking the plunge with us. We'll see you on the next deep dive.